All right, welcome everyone to a new Quantum Matter seminar. It's my pleasure today to introduce Sasha Alexander Chernyshev from UC Irvine, who's going to give us a presentation on his latest research on quantum magnetism. I want to make sure that you all know that you can unmute yourself at any time and feel free to ask questions. And otherwise, you have time for that at the end of the presentation. And you can also post your questions on the chat and I will read them for you. All right, Sasha, welcome. Go ahead.
Yeah, as I mentioned before recording has started, it's actually a great pleasure to attend such venues nowadays. It gives a sense of normalcy, and many thanks to Adrian in this case for keeping it up through the summer and giving me this opportunity to speak. I'm going to talk. This is not the most recent. I wish I could talk, have time to prepare something more recent. Some of you may have heard pieces of it before. I'm going to talk about some work we were doing in the last maybe 3 to 4 years. And it's about a rather old problem, which is a triangular-lattice antiferromagnet, and she has been around for quite some time. That's why again is here. And what I'm going to do, I'm going to try to convince you that there is a new twist on this old problem introduced by a variety of materials, which appeared about 5 years ago with similar structure to the one shown on the right. And I guess the rough and most important outcome is in the form of this cylinder, which I'll explain later what it is. It's basically a phase diagram of this what I would like to call an isotropic exchange antiferromagnet. Okay, so the plan. I'm not sure. I need 2 hands to operate this device now. So the plan is have some form of historical overview and maybe introduction for those who are not experts. And it's by no means a comprehensive historical overview, but I hope I will provide even experts with some insights which are lesser known. I'll then spend a few minutes on saying what these new materials were, and then share our insights, however briefly. Okay, so the argument can be made that whenever you hear talk about frustrated magnetism, it always begins with a picture of a triangle. So I'm sorry if you've seen it already too many times. So the idea is that if you provide certain rules, and rules in this case are the following: that you have spins which are Ising-like, meaning they can only point up or down, and they want to arrange themselves in an antiferromagnetic fashion, meaning the blue connection between them is a happy one, and you put it in a triangle, you cannot satisfy simultaneously all 3 bonds. You can only satisfy 2, and the third one will be unhappy bond. And this has been first realized about 70 years ago by Gregory Vanier, who wrote this paper, and which stated that there is no unique ground state in this geometry on triangular lattice. The deeper and more important implication is actually that the entropy is at absolute 0 is finite, meaning that actually there is a massive degeneracy of such a ground state, and this is the most important the outcome, which has lots of implications, that frustration can and often does yield degeneracy. So in a kind of rather simple-minded upshot, if you imagine a so-called bipartite lattice, like square lattice, which is unfrustrated, you have a non-degenerate ground state. You have only doubly degenerate ground state. You can either have spin up, down situation, and all bonds are happy, or you have down, up. So that's a double degeneracy on the left picture here for the density of states, and then the H-excited states is just a spin flip with a certain gap. While in the frustrated case, in the Ising case, you have a degenerate manifold of states, which is exponentially degenerate, and n being a number of sites in your system. And each excited state is also highly degenerate. So again, maybe stepping all the way back and maybe stretching this analogy a little bit, one can say that one can argue that this is the degeneracy in this case is a very good thing. And I want to use this analogy from sort of high energy physics, where there is an idea that our universe is governed by a theory which has so-called grand unification scale, where h bar becomes equal to g, to the gravitational constant. And this scale is way up there. It's some orders and orders of magnitude higher than anything we are dealing with at lower energies. And yet we know that lots of interesting stuff is happening at this low energy. So the parallel I want to draw here is that massive degeneracy at the bottom. We have everyday evidence to that there's lots of possibilities. And there are some other, maybe again for the experts, there are forms of order which are more creative, which can occur, which are not coming just from the sum of the properties of the constitute particles, and that's kind of the broader idea of this game. And for the spin systems, the idea is that you can use this, you can play this hierarchy game using spins as building blocks. Okay, and that's again kind of overarching, kind of an umbrella for the whole activity. So as I promised, there are maybe a few curiosities even in these old papers which are not known even to the experts. So the first curiosity I want to show you is that it's in the abstract of that paper by Vanier, where he shows this integral, and maybe some of you may even be able to type this integral in Mathematica and take it and verify quickly what I'm going to say. But so there is a number here. And it's also a lesson for students and postdocs, and not only for them, that it's never late to write an erratum. So 23 years later, there is actually an erratum by Vanier, which corrects the second significant figure and on because the series expansion failed, or he failed at the series expansion back in the 1950s. And the rumor is that in the meantime, some numerical methods were benchmarked against the original wrong number. Okay, so this is the second part of my introduction, maybe not as bright as the first one. And it's a story, again, intimately connected to the triangular geometry. And there's this series of work by Phil Anderson and also in collaboration with Patrick Fazekas on the case of the Heisenberg spins. And it was a proposal which set off the whole activity on the so-called spin liquids, and this was a proposal of a specific kind of it, of resonance, what's known as resonance valence bond type of spin liquid, in which spin 1/2 in this case, Heisenberg ones, they do not want to order. They refuse to order. Instead, what they do, they form local singlets. So each of these ellipses is a singlet, a linear combination of spin up and spin down. And they arrange themselves in the lattice, and this arrangement actually fluctuates. Okay. So the curiosity here is a little deeper. So if you open the paper by Anderson, it's actually, you find that it has been devoted to some celebration of Linus Pauling, and Linus Pauling actually was credited for introducing this idea of fluctuating bonds, because he first proposed it for the benzene ring, right? For the carbon bonds in the benzene molecule. And however, the curiosity here is the following. So Pauling is, and this connection is well known. So Pauling is cited here together with Rumer. And the citation to Rumer also goes to the journal, which you will have very hard time finding in any library. In fact, almost no library will have it, except for Göttingen. So the question is, who is Mr. Römer? So Römer was actually transliterated in German and Russian, and I'm sorry, in English as George. So his original name is Yuri. He spent some time in Göttingen in the 30s, and you can see this is actually the paper which is quoted in Anderson's paper, and this is the paper on the same year, co-authored with some famous people like Teller and Weil. You don't need to be an expert to recognize that those pictures have some relevance to what Anderson was talking about. And in fact, you don't need to know German, but this title explicitly tells you that it is a theory of valence of spins. So it's all kind of highlighted in the abstract of Linus Polling's paper, which says that, which credits Römer for discovery of the language of valence bonds, of the representation, of the complete representation of valence bonds. And that's basically his contribution to the whole story. Then Linus introduced idea of fluctuating bonds, and then Anderson has generalized it to the spin systems on the triangular-lattice. So that's a full story, almost. You may wonder why you never heard about Römer before, and this is at least partially because his life was interrupted in an unusual fashion. Some of you may recognize one more gentleman on this picture on the right. It's kind of, on one hand, rare, on the other hand, a well-known picture of Lev Landau when he was in jail, arrested on the alleged conspiracy to overthrow the government, and he wasn't alone to be arrested. His close friend Römer was arrested as well, so as the third gentleman here is Korit. So they were all jailed, and Kapitsa was able to pull out Landau in about a year and essentially set him free, while the rest of the gang has spent quite some time in what's referred in Russia as the places not too far away. And Römer in particular spent some 10 years in what's referred to as Sharashka, in like Gulag institutions. So he remained in Siberia after some exile and was the founder of one of the theory groups there. And the reason why I'm particularly sensitive to all this, because I spent some years there and actually was in, I collaborated and talked to his former students and colleagues, and that's his flag there. So the reason I'm showing all this, that sometimes it just, it's worthwhile to dig a little bit deeper and maybe to give credit to people who are often not credited for what they have originally invented. Anyhow, with this on this positive note, let me move on to a little bit more modern times. So rare earths occupy big part of this line over here on the bottom, which doesn't fit in the periodic table. And actually, maybe another curiosity, because this year or last year was the year of periodic table. Mendeleev stopped working on his periodic table because of rare earths. He just couldn't figure out where they're going to be fit. So that's another curiosity here. But rare earths, of course, are well-known materials as heavy fermion materials, and maybe also, related to some form of conducting materials with anomalous properties at low temperatures. But I think this particular material, ytterbium manganese gallium oxide, was the first quantum magnet not from the family of pyrochlores, which was synthesized. Maybe I'm wrong, but this at least this is all I know. And it grows in large sizes. It forms nearly perfect triangular-lattice layers. It's rigid material. It can be grown large. Lots of experiments can be conducted and all that. And the family I'm going to mention later, they all have very similar structure when the magnetic ions are surrounded by the octahedra of different ligands. In the case of YMGO, this is how it's abbreviated. In the case of YMGO, it's an oxide which is sitting around magnetic ytterbium ions. So after that, maybe a year and a half later, there was a family of chalcogenides with oxygen, sulfur, and selenium can be substituted with, again, the later iteration contains other alkali materials and all that. There's a cerium series by now, and last year there was a flood of materials from both Bob Kava's group and from Oak Ridge. This is a picture from Oak Ridge group, and I think those are from a different paper, also from the Oak Ridge group. And the beauty of rare earths is that you can essentially substitute one rare earth for the other with chemically with very little problem. Okay, so that creates a job for a theorist to understand maybe there is some commonality to their properties. Many of them don't order magnetically. The question is why. And the first question a theorist would ask here is, what's the phase diagram? Okay. All right. So this is a claim that we have studied the most general with an asterisk nearest neighbor anisotropic model on a triangular lattice. I'll explain why it's only nearest neighbor. I'll explain what it means by most general. And the appeal of that problem is the following. Rare earths by nature contain a lot of what's discussed under the umbrella of spin-orbit coupling. It basically has very strong spin-orbit coupling within each ion. Okay, and that's new way or newer way of providing competing interactions. So this is the way of providing more conflicting terms in your Hamiltonian. This type of interaction is combined with the more traditional geometric frustration, which I introduced before. Basically, you know, the triangular geometry in itself is frustrating. So the question is there something interesting there? Or in general, what just comes out? So for the experts, those bond-dependent terms can be referred to as Kitaev-like because of the history of d orbital materials, where the spin orbit effects are also strong and well studied and well known by now. Okay, so the one asterisk, this is actually one of the explanation what most general means here is actually structurally ideal one. The second asterisk will be that it's a certain range of parameters still very restricted for the physical reasons. And the claim is that we have provided, together with other people, we built on some other people's work as well. We provided a comprehensive description of this model and described some of the phases in a little bit more detail. So by us, I mean Zhenyu Zhu, who is working for AI now, and Pavel was is now my former student. We keep collaborating. We can't stop collaborating. He's now back to Dubna for already a year plus, so a little more. And Steve White doesn't need an introduction. So those publications, we started with studies of disorder in this particular material, and then kind of branched out on the problem I'm going to describe, on the problem of nearest neighbor phase diagram, and actually some extension of it as well. You can see that there are some funny words used in each title, and so we refer them as to mimicry, topography, and duality papers, but I will be mostly spending my time on the middle one and a little bit on the last one, and just a few words about the first one. Okay, so this is kind of important slide in a sense that I'll spend some time on it, advocating why this is the common situation here. So generally, again, you're dealing with rare earth ions, and I'm this asterisk is used now to say that I'm only going to look at Kramer signs, meaning that my total magnetic moment is half integer. Okay, so example is terbium-3 plus, which has 7/2 orbital moment, a complicated mixture of orbits and spin. Okay, so what do you do with it? And it's basically problem reasonably hard to solve, not for a system of such ions and how they couple. But what helps sort of low energy understanding of the low energy physics in them is the effect of so-called crystal field splitting. It means that those ligands which are around, right, those oxygens which are sitting around and some other ions which are sitting around, they provide a sort of a cage of charge, which pins roughly speaking, it pins that complicated orbit in a certain way. And it leads to splitting the levels. This is not the most gorgeous picture of it, but this is a neutron scattering for split levels. And each one of them is a doublet, because Kramer's degeneracy requires doublets to stay degenerate. What you are not seeing here is the lowest doublet, and the lowest doublet is our ground state. Okay, so each and every, so these doublets are some form of projection of this enormous Hilbert space on the lowest doublet manifold. Okay, so they and that's a huge simplification. So we end up having effective or pseudo spin 1/2. Okay, but then the question is, how do they interact? And in general, if you just put atoms next to each other and ask this question without providing any constraint, the answer is that, well, you can have up to 9 different terms in your exchange matrix. When spin 1 talks to spin 2, this effective spin, then it's going to contain up to 9 different terms. That's the price to pay. Compare it to the Heisenberg model, you only have diagonal terms which are all equal to each other. Okay, so just to set expectations. The second thing which simplifies things for us, or for everyone, quite a bit, and this situation is actually quite common and also in other geometries, is that this octahedral environment and this the symmetry, the rigid symmetries of the lattice, the point group symmetry of the lattice, cuts off quite a bit of this zoo of exchanges here. In fact, what it tells us that you cannot have, for instance, on the triangle lattice, you cannot have antisymmetric terms. All the off-diagonal terms must be symmetric. And then you end up with just 4 terms. 4 sounds like a reasonable number to deal with. Last simplification, compared with many other systems in like copper-based and any transition metal materials, is that it's mostly nearest neighbor exchanges. It's very hard for the characteristic energy scales are rather small for those J's. It's they're of the order of kelvins, and the interactions beyond the second neighbor are essentially non-existent, and even second neighbor is quite small. So you can convince yourself that the model is just nearest neighbor interaction between spins with the matrix, and matrix contains 4 terms. What's written here is the matrix for the bond along the x direction in the axis where x and y are within the plane of magnetic ions, and z is pointing out. Okay, so then everything looks reasonably simple, and all you need maybe to make it more humane looking or more familiar looking than it is at the moment is use some form of parameterization. So let me just show you the answer and tell you what this parameterization implies. So the answer is that you have 4 terms, and I've chosen the first 2, the coefficient in front of the z term is in units of coefficient in front of xx and yy. So I introduced total j and delta. And some of you may be more very much comfortable with this language, but because this is the usual way of writing the so-called xxz model. Okay. You
Sasha,
can
just an interruption. Martin has a question. Let me allow him
Martin, sure.
to unmute himself so he can.
I can see Martin though, so let me.
Hello,
no.
can you hear me?
Thank you.
Hello?
We can hear you. Yes.
Okay.
Yes.
Okay, thank you. Yeah, so I have a quick question. To constrain the spin model, do you take into account the magnetic point group or the crystallographic point group?
It's just crystallographic point group.
Okay, and there is, so what's the reason for that? How can you, I mean, what allows you to not take into account the point group and the magnetic point group?
Okay, so all I'm using, okay, let me just say what I'm using here. Okay, so I think what's used here is that you have you can take this bond and rotate the whole lattice by 180 degrees, and it maps on itself. Okay, so that makes that's what makes these four terms go away, because this essentially tells you that the Hamiltonian must be the same. So it's basically like you're looking from the bottom of the plane or from the top of the plane. The physics shouldn't depend on that. Okay, so that's
Sasha.
Yeah.
May I answer this question a different way? Probably will be more helpful.
Okay.
Point is that the Hamiltonian that Sasha is introducing is before any magnetic order sets in. This is the assumption is that Hamiltonian does not depend on magnetic order itself. There might be some sort of feedback nonlinear issues, but they are not considered. We think that Hamiltonian defines the system. And because we don't know what magnetic order will emerge, obviously Hamiltonian cannot depend on this unknown magnetic order. Right, Sasha?
I wanted to come to that slowly, Igor. Yeah, but thank you. Yeah, thank you for making it short. Yeah, thank you. Is it okay, Martin? Okay.
Thank you.
All right. All right. So all right. So the okay. So you can see two groups of terms. First two I described this as XXZ model, and the other one is the terms which are for historical reasons going back to pyrofluors. They are referred to as J++ and JZ+ terms. And you can see they have some complicated angles, but those are angles obtained from the fact that you actually require all the bonds to be equivalent. And therefore, your original matrix, which is written on top of the slide, you need to rotate it by 120 degrees and 240 degrees. And those are the angles of this rotation. Okay, so these terms explicitly tell you this is where the origin you can see traces of spin orbit coupling. They are telling you that bond orientation through this cosines and sines of these angles, bond orientation, those orientations of the bond. The bond orientation is coupled to spin orientation in one way or the other way for these two terms. Okay, all right. So this is the origin of this Hamiltonian. You can write it this way. One more asterisk, and I think this is the last one. So the one we were mostly focused on was actually the so-called, actually that's what referred as the XXZ or easy plane part, meaning that delta, this coefficient here is between 0 and 1. First of all, it made much more sense to us because some of the observed phases were related to the known phases of the XXZ model. And second, most layered systems actually do fall in this category, not all, but most. So there are, of course, other cases, and some of the phase diagram actually survives. Some of the phases I will discuss survive in those cases as well. Okay, all right. Finally, to the business. So this is the model, and it's again written in this axis where the y and x are within the plane and Z out of the plane. Why am I mentioning that? Because in principle, you can use a different parameterization. And the different parameterization, which is actually rather popular nowadays, is to use different axes. Is to use axes which are associated with the, I'm not sure if you can see my mouse. So this is, those are the bonds connecting magnetic ions with the perfect cubes of the oxygens forming around it. And if you use this triad as an axis, you actually can rewrite the model in a different way. And this is referred to as generalized Kitaev model. And I'm going to, I'm going to use this connection sometimes later in the talk. Okay, so that's just a statement. In principle, both models are valid. This is just a different parameterization of the same exchange matrix. Okay, and one can be more useful than the other, and I find the ice-like, the one I introduced originally, is much more transparent physically than the other one. Of course, if you're looking for Kitaev physics, the second one is more appropriate, but on the triangle lattice, there is no Kitaev solution, so there is no reason to use it a priori. Okay. Again, this is an upshot of what's going to happen in the second half of the talk. Is the phase diagram requires 4 parameters. One can be used as a global scale. Let's say J is a global scale. Then you have 3 parameters. Therefore, you have 3D phase diagram. And this is how this phase diagram may be drawn in a compact fashion and rather informative in our humble opinion, where delta is a vertical axis of the cylinder. And bottom, therefore, bottom of the cylinder corresponds to XY limit, and the top of the cylinder corresponds to the Heisenberg limit. The parameterization of the face of the cylinder is through parameterization of J++ and JZ+ terms, the bond-dependent terms. JZ+ is parameterizing the radial component here, and J++ parameterizing the polar component. And it's some of the phases here are very easy to understand where they come from, because there are these 2 points, for instance. These 2 points correspond to the case when both J++ and JZ+ are 0. And it doesn't matter which delta you choose. If you choose J negative, you end up with a ferromagnetic state. And of course, it's stable in a finite region of parameters around it. And the south pole here, because of the sign convention we have chosen, the south pole here is where the 120-degree phase resides, the one with which corresponds to the usual ordering of spins on the triangle lattice. There are 2 other limits here, for instance, when this is where the point where only J++ term is present. And the pole which is in the center, if you think of this circle as a squashed hemisphere, so the north pole of that hemisphere is actually where a JZ+ term is the only one present in the model. Okay, all right. So that's basically will be the answer. And so let me now. Okay, so the propaganda is, of course, that we should be able to take each of these materials and given enough experiment.
Sasha, could I ask a quick question?
Yeah, sure.
On the previous slide, there were some small regions that looked like they were spin liquids.
Oh, yeah. So I'll spend some time on them. So yeah, so those are results of some DMRG calculations I'll talk about.
Okay, I guess the question I was going to ask is whether further neighbor interactions would lift that generously and maybe break the symmetry. Please wait.
Okay. In fact, there was an interesting connection to the J1, J2 model. Okay. All right.
Okay. Thanks.
Now, I just want to give, everyone who will be not too eager to hear all the technical details to some message kind of rather upfront. Okay, so again, the idea is that we should be able to go back to the materials and tell where they belong, provided we have enough experimental information. Okay, so how much time do I have, Adrian? Like 20 minutes? 25? he left.
You can speak as long as you need. I don't think the audience is going to complain. I mean, some of us may have to go to other things, but
be done in a time.
It's okay. I think 30 minutes.
Yeah. Okay. So I'm going through some technicalities here, which is again just maybe to explain some parts of our thinking, but I'm not. I'm trying to skip some others as well. So again, in this business of sort of unknown, right? You deal with a model which you haven't dealt before. You want to ask what each of these terms in the model, what does each term want? Okay, and I explained to you what XXZ term wants. It wants to be in a 120-degree status in XXZ triangular-lattice case if delta is between 0 and 1, and J is positive, and if J is negative, it's a ferromagnet. Okay, so this is easy. The bond-dependent terms are a little bit trickier. So if you look at so let's pick this term and just J++ term and ask what does it want along this bond, along the horizontal bond, and that's a form of the coupling along this bond. It's very simple. Let's say J++ is positive. So you say, well, then spins probably will want to align along the y-axis and both of them. So in a ferromagnetic fashion. But then a little bit of thinking tells you, no, wait. They can also align antiferromagnetically along the x-axis. And actually you figure out that anything in between will also work in the form of a counter-rotating spiral. So this is actually known as some form of hidden U1 symmetry, because you don't necessarily there's formally no continuous symmetry left in the Hamiltonian. And I just want to know that actually some of the iridates on the some extension of the honeycomb lattice, they actually do exhibit counter-rotating spiral configurations in the ground state, and those were rationalized in terms of Kitaev-like terms, but this is, I think, is much simpler explanation. And the honeycomb lattice is bipartite, so it's not further frustrating as a triangle lattice, because here on the triangle lattice there are two problems. It's not a bipartite lattice. This is number one, and second, so spins don't want to sort of break into up-down sublattices a priori. And second, you have different directions of the bonds. So these counter-rotating spirals along each direction, so along this direction, along that direction, and along this direction, they will conflict with each other. So what you end up having is some form of locking of most probable state. And these states are up to six-fold rotation. They are degenerate, but the negative J++ will give you the stripe phase. With stripe means the state with the ferromagnetic looking rows alternating with antiferromagnetically with the next row. And if J++ is positive, this is actually a stripe YZ, but I'll name it later on the next slide. So this is kind of the logic you go through. So let me skip the details of the last term, JZ+, only to say that it actually provides the same kind of insight with the counter-rotating spiral with a different pitch, if you want. And what it wants spins to always align perpendicular to the bond. So it's actually in accord with the positive J++ term. Okay, if J++, J++ is positive, then this JZ+ is in agreement with that. They both want to have spins in this configuration, that's stripe YZ state. What the other dimension this term provides is actually tries to tilt spins out of the plane. All right, so that essentially gives you an idea where this majority of the states I described come from: ferromagnetic, stripe X, stripe YZ, and 120. There's one remaining piece here, which is the 12 sublattice state, which is the some configuration obtained from 120-degree state by some rotation of spins. It's just a little bit more complicated state, but it's still single Q state, meaning that there is an ordering vector and it's a single ordering vector which is associated with each one of these 5 states. So this is, you can sense that this is may not be necessarily the full truth, but this is like 99% of the truth. Okay, so this phase diagram is approximate phase diagram, but it's actually it works for the majority of this phase space. So this I highlight this white line just in case I have time to speak about that. This line actually corresponds to the, or actually it's a fold throughout the whole cylinder, is where only J++ and JZ+ terms are present. Why do I need that? Well, because originally, of course, people were looking for unusual exotic states here. And the question is, how do you do that? How do you look for spin liquids? And I'm told this book is out in print, but I couldn't find it in Irvine library. So we had to go without it. And the usual logic is, the conventional logic is you look at the ordered phases and see if you propose the state and you check whether it's stable to fluctuations. Or maybe you check the boundaries and see if there are some additional phases lurking at the boundary. There is another logic which comes from sort of inspired by Kitaev's solution, is that crank the most anisotropic terms, crank them up as crazy and see what happens. Okay. This second, which is listed first logic here, is actually didn't quite work, but for a while we were convinced that there might be something related to that, but then it has proven to be in kind of an empty hole. All right, so let's pursue this route of quasi-classic stability and cut that cylinder at the half height, at delta equal to 0.5. So we can find all the states, all the ferromagnetic 120 stride states, and calculate the ordered moment. And we calculate the ordered moment for spin 1/2, including quantum fluctuations. What you can see is the color bar here next to that circle, which emphasizes how big that ordered moment is, including fluctuations. And you can see that it's hardly declining less than maybe 0.36 or something. And the rest of the states, I'm sorry for this language, are deep red states. The blue states you see here is the one which is dual 120. We just didn't have power to calculate something. It was just too much for us to calculate ordered moment for the 12 sublattice state. But there are these two kind of wedges here which allow for maybe additional intermediate states. Those were suspects for a while. Turns out, and again, this was figured out somewhat before us, that these states are also quite highly ordered. What they constitute some form of intermediate state between some modulation of stripe phases. Okay, so those are referred to as multi-Q states. The second kind of search for stability went of these quasi-classical states went actually after we found spin liquid, but for logical purposes, it's actually this is how in an ideal world we should have proceeded. So in an ideal world, you start with the picture I have shown you and focus on the 120-degree state and look for stability of excitations. And actually, you find that excitations of the 120-degree states are stable way beyond the 120-degree phase itself, which is a recipe for the first order transition between stripe and 120-degree states. But this is for delta 0.5. So when you start decreasing or increasing delta, decreasing the anisotropy towards the isotropic limit, you discover that actually there is the 120-degree state becomes unstable in this direction. This direction is the direction of JZ+. And it was a puzzle for us for a while, but again, someone talked about that before, that it's actually another multi-Q state, which is a complicated form of a spiral with like three spirals meshed together, the so-called Z2 vortex state. Again, this was chronologically not quite what we saw. Instead, we actually run across, thanks to persistence of Zhenyu, that we run across a spin-digit state actually precisely in this region near 120-degree state. But that required DMRG, and this is how it was pioneered, I think, in Steve's group some time ago, that you can actually do the following trick for a reasonably quick shot at the phase diagram. You want to have one-dimensional cuts through the phase diagram. Basically, you fix all parameters and vary one of them. And you make a cylinder rather long. So some of the cylinders were up to 40 sides long, and the circumference can vary, but not by much. But scanning like this actually provides you with immediate clear picture whether you have a suspect for the disordered state or not. And I'll demonstrate it quickly, because this is, again, this is not what I'm doing for a living, but again, this was an essential part of our finding. So again, you can employ on top of that. So on top of that, you can employ other measures within the DMRG approach, which may be more familiar to some of you. But let me demonstrate how this cut would look like. So what I'm showing here is the cut along the border of the edge of the cylinder in this direction, which is in Cartesian axis. It's here. Again, this is quasi-classical phase diagram, delta 0.5. You don't need, to consult with your lawyer to conclude that this is direct transition of 120 to the stripe phase, and this is kind of there's nothing to look for here, and you can change the values of the other parameters, scan in different directions, and again, what you can see is just migration of the border between the phases, which is consistent with the quasi-classical phase diagram very closely. This is a different cut, again, same type of transition, close analysis using not long clusters, but clusters of fixed parameters and smaller size. And so this exploration essentially leads to close agreement between some prior exact diagonalization work, which used some small clusters and fidelity measurements, and DMRG and quasi-classics. This is for delta 0.5, okay? So again, this is persistence of Zhenyu, who basically wasn't convinced that this is all, and he went on. And so some of the cuts do look like I described before, direct transitions only between one type of the stripe phase and the other type, the X, stripe X and YZ. This is along this line. But then performing this cut, he found that the order is suppressed quite a bit. Maybe not so convincingly that to suspect a spin-digit state, but he checked this direction. He checked the vertical direction first, and then he started feeling that there is something there because there is a kink and there is a transition, possible another transition. And then among other things, what sealed the conclusion is that if you check the decay of the correlation length within the cluster, it's from, if you fix a spin at the boundary, kind of to try to induce an order in the system, it actually falls off exponentially, which tells you that the system is not going to support the ordered state. Okay, so to make this already a little bit longer story short, the spin-digit region has a footing on the top of the cylinder in the Heisenberg limit, and it's wedged within the cylinder up to certain lengths. And again, this cluster may be even more convincing than the previous one. You can see this is scanning from the middle of the cylinder to the top of it, and you initially see the order, which then disappears at about 0.75 for sure. Okay, so there is a region of spin-digit here, and we can draw it slightly differently. This is the 3D or topographic map of this spin-digit, with the backdrop is J++ and JZ+, the anisotropic terms. And the axis which is pointing towards you is the delta axis. Okay, so the footing is again the largest extent of the region is at delta equal to 1, and it sort of disappears at about 0.67, something like that. But it forms the region which is like a deformed tetrahedron. We can basically pick some points and look at the signature at the characteristics of this spin liquid. And the way it's helpful is because it shows you where the maxima in the structure factor, in the basically the correlation function of spins is. And the correlation is near the K points, at the K points. It's exactly where the 120-degree phase would have an order. So it would be a sharper peak. And in fact, this is related to what Greg has asked me before. This is not different from what people observe in the Heisenberg, not anisotropic, purely isotropic J1, J2 model. Okay, so we started looking into that. So I ran through the history part rather quickly for showing some unknown pages, but the one thing I failed to mention is that J1 model, J1 only model on the Triangular-lattice Heisenberg limit actually doesn't support a spin liquid, and that has been sealed in the end of the 90s, early 2000s by numerical techniques. But what was discovered later is somewhat unexpectedly in 2015 that actually the J1, J2 model, isotropic J1, J2 model has a spin liquid state in this region of J's. So this is a one-dimensional phase diagram drawn in a funny way. J2 is in units of J1. And you can add this delta axis here, which has not been looked at before our first paper. And that's how the spin liquid region would look like. So the footing is this 0.6 or 0.15 or so, and then it actually extends quite high in terms of delta. So it extends almost up to XY limit, but not quite. Okay, what happens if we start adding the J++ term here? Not JZ+, but one of the anisotropic terms. And that's what happens. It actually kills spin liquid rather quickly. So if you go along the J++ axis here, so the bottom portion of this graph is showing you a topographic map on different axes. I threw away one parameter. I threw JZ+ parameter, but I kept delta, which is here in XXZ, and I added J2. So I'm still dealing with the three-dimensional space, and you can build this, three-dimensional map out of here. Again, it's some deformed tetrahedron of some shape and of some sort. It was actually supported by a variational Monte Carlo work by Leon Ballen's group a year later. You can see the blue region here. It's a footing of our spin liquid phase, and then this cut is about half the height, and then there is a small tip over here, which is the cut about here. So numerical evidence is an agreement to the fact that the well-known, rather well-known J1, J2 model extended to the anisotropic model, and in the both XXZ direction and J++ direction, actually still supports spin liquid state, but both anisotropies are actually detrimental to it. Okay, you can see that I sneaked in the fourth dimension of the phase diagram. So I have one phase diagram, which is a backdrop with the topographic map, and I have a bottom of the phase diagram with a different topographic map. The question is, and that was the question of Greg, I think, implied, is there any connection of that anisotropic spin liquid region to that isotropic spin liquid region? Okay, and classically, you can complete this phase diagram classically for fixed delta, right? You fix delta, and then you back to a three-dimensional world. Then you do have, 120-degree phase has this shape in the phase diagram. And if there is a connection, it is sort of along this rim of the 120-degree phase. So again, time for a little bit more DMRG. And this is the cut, the long cylinder cut from the anisotropic spin liquid to the fully isotropic spin liquid. These are the pictures of the structure factor from different regions of this cylinder. So basically going from here, here, and here. You see no difference, roughly speaking. If you compare the correlation function, it actually differs by maybe 5% on average, but it's basically the same. We refer to it as isomorphism of spin liquid. So basically that anisotropic spin liquid which was found is isomorphic to the one known for the J1, J2 model. Maybe it's a little bit disappointing, but it's at least it tells you that you learned something. Okay. All right. Yeah. So we also checked some other
question about that. Is there another way to check, like you showed this correlation length with an exponential decay of the spins in the boundary in the spin liquid phase? I assume that means it's a gap spin liquid.
Okay, gap.
Then can you show the gap doesn't close, for example?
Sure. Okay, so there's I'm wondering who was our referee now. Yes, so I don't have that picture. I have a different one. It's just basically correlation function like S, I, S, J along certain complicated paths up to 11th neighbor, and they're all the same for all three regions. The question you're asking is different, whether it's a gap spin liquid. DMRG on this geometry will always give you a gap spin liquid. It's a question to the technique. And it's known in the Kagome case when you need to use sophisticated boundary conditions and introduce fluxes in order to modify your k-space in such a way that you actually zoom on the kind of ordering vector, and you can show that at least in the Kagome case, this gap closes. So basically, it's gapped in the J1, J2 case, right? Mm-hmm. As it seems from the DMRG. It's known, though, that there is a recent work by, I'm missing his name, he's at, I hope he doesn't listen, but so there is a recent paper I can refer you to, which actually checks, and this is indeed on the Triangular-lattice. The answer is that it's also gapless, but it's a Dirac-like. Okay.
Okay. So you're saying the DMRG can't answer the question of whether the gap doesn't close.
Not straightforward DMRG which we were using. So you need more tricks, and you need more time, and you need Michael Zaletel to do it. So
okay.
All right.
Thank you.
So the point I wanted to maybe mention that there is come on. There are always questions whether we are missing some other orders, and both chirality, which this quasi-classical analysis of the Z2 vortex state actually imply there may be a chirality order there. There is no chirality to very high order of accuracy. There is no valence bond order as well, to maybe lesser accuracy, but I think compared to the other cases where valence bond was detected, it's basically below the threshold of detectability. Okay, let me rush through this quickly. So there is this connection, just different language of rewriting the same model. Okay, and in some cases it can be beneficial, and this was the case when it was. So the people who study Kitaev-Heisenberg model, they don't like these terms generally, and they try to throw them away. So let me play this game and throw this away. Then you're left with just two terms. It's and then you have two parameters, and you can ask, where does it live in this cylinder? It actually lives on the surface of the top surface of the cylinder and the Heisenberg limit, and it forms this ellipse here. So the K only points are here, the J not points are here, and all that. And the beauty of this model is that there is lots of redundancies in it. Okay, and one of them is emphasized by existence of simple dualities, which I can talk about, but in this case it was a little bit more complicated duality, which requires local transformations of spins, rotations of spins on 3 sublattices out of 4, and what they lead to mapping of the model on itself, but in a different part of that circle, of that ellipse. So basically, the language here is that there is a region here in this completely entirely in the stripe YZ phase, which is dual to the entire part of that circle which belongs to the ferromagnetic state. And actually, this is a rather powerful statement because you basically say that up to certain transformations in the Q space, all physical properties in zero field of one region, of this region are equivalent to the properties of that region. I can talk about that later if needed. But what was important for us is that there is this other part of the circle which is dual to that other smaller piece of the circle. Why it was important? Because the original part of that ellipse actually crosses through the spin liquid phase. Therefore, there should be a dual part of the spin liquid here. Okay, so we zoomed on this region. There was more of DMRG work needed in cuts in different directions and all that. And this was the point where we were strongly suspecting that this might have an exact solution. And we asked some collaborators to check Tower of States, and the Tower of States unfortunately turned negative, meaning that the model is not integrable, and therefore exact solution is unlikely to exist. But what we found is essentially what you expect. The 120-degree phase has peaks, characteristic peaks at the K points over here. The dual 120 phase has Brillouin zone, which is 4 times less in the area. Therefore, the ordering vectors are half of what you have for the K points. And that's exactly where we observed broadened peaks. So if the original spin liquid was molten 120-degree state, this is a molten dual 120-degree. Okay. I need 2 more minutes to go through the sort of physical part of it, and then I'll be done. So the original material was a suspect for spin liquid because of broad peaks and no ordering and all kinds of other things. And at the same time, there were 3 strikes against it. First of all, the features in spectrum remain broad, even in above the nominal saturation. There was no detectable thermal conductivity. Freezing was discovered eventually, and the last strike was actually the first and most important strike was that there is a mixture of not isovalent ions, about 50-50 substitute mixture of magnesium and gallium in these planes between the magnetic planes. So there is a disorder in the system, intrinsic disorder. And again, making a long story short, we had this paper in which we advocated the following picture, that you can have an ordered state, which is nevertheless fragile to the rather weak disorder, which turns into, as was argued later by, again, Balance group, that this disorder type is necessarily of transverse field type. And therefore, you always break the order into finite domains, and therefore, what's observed in YMGO is the disordered mimicry of the spin liquid state. Okay, and maybe yet another argument is that nowhere in the phase diagram the peaks which are observed, intensity peaks which are observed in S of Q experimentally, are the M points. This is where the stripe phase should have a peak, ordering peak. So it's more like molten stripe phase, not the molten 120-degree phase. And there is no spin liquid in real model, if you wish, where there is a spin liquid which would have such features. Okay, all right. So YMGO is in the stripe phase, which looks like a spin liquid. There are other materials which are introduced recently. This is one of the example of the one of the chalcogenides, and it shows the broad peak in the zero field at the K point. All points to either 120-degree phase, which is disordered by remnant impurities, or it's actually somewhere in that spin liquid region, which we have found. What's been analyzed in much more detail nowadays are the field dependencies of field evolution of such disordered phases, and most of them quickly order into something else. What else is not quite clear, but maybe near future will show a little bit more detail. Okay, so there are other materials. There is one more material I worked on, and it's still waiting some response from experimental colleagues. And this the cerium compound shows a well-defined gap, and by the field dependence of this gap, we can actually pinpoint. This is probably the first case of the whole family where we can tell where the material belongs in terms of parameters in this extended phase diagram. And I'm just highlighting. I cannot show you experimental data, but basically those are narrow strips of parameters where this material has to belong to. Okay, I'll skip that, which is actually something Christian Batista should know. And there is an additional way of identifying where the material belongs using the high field data. And what we have found following some of his recent work, is that there is a tendency of the 3 sublattice order, which is traditional, triangle lattice behavior of antiferromagnets in a field, to overcome the tendency of the 4 sublattice order, which is characteristic to the stripe phases, as a function of the field. The vertical axis here is the field, and therefore high field phases for some part of the phase diagram actually do look like they belong to the original family of the field polarized antiferromagnets on the triangle lattice. Okay, so let me stop here. I'm a little bit over time, but I hope you liked it. That's it. Thank you.
Thank you, Sasha, for a beautiful talk and for summarizing so much of your recent work. And it's now time for questions. So the session is open. So please feel free to either raise your hand or just unmute yourself and ask directly.
Okay, Sasha, may I ask a question?
Sure.
You just stressed specifically that in this model, there is no place neither for valence bond solid nor for these chiral phases. I just wonder, what could be the minimal modification of the model which would allow any of those, especially chiral? Maybe just, I don't know, changing somewhat symmetry, allowing for the Lashinsky interaction or whatever.
Okay. So
Minimal. What would you anticipate? What you guess?
It's interesting because in principle, quasi-classically, the model does allow you the Z2 vortex state, which is chiral. So the truth of the matter found by unbiased numerical results is that that spin liquid phase is not carrying any memory of that. It's an entirely different state, basically. So it's it's basically you can simplify this model to this JK model in a triangle lattice, and it will have this the chiral Z2 phase quasi-classically, but not for spin 1/2, not for quantum mechanics. I don't know, maybe going larger spins, but not. I doubt. It's a question whether it will be a liquid state in this case.
What about some modification of symmetry, for example, removing inversion symmetry so that the Lashinsky Moria would be allowed or whatever?
Right. So if you start with distortions, I don't have just distorted triangle lattice will support some form of deformed spirals, but those are not non-coplanar states.
No, I don't mean the distorted triangular lattice. The triangular lattice may be okay, but say some other ions in between, or maybe between the layers, which would remove some of the symmetry elements. It would allow for example, for antisymmetric exchange. If you just change the symmetry, somehow just not making this kind of uniaxial or distorted triangular lattice, but simply just every bond lose inversion symmetry, for example, due to some other ions, due to doing something with some other ions.
Right. No, we haven't spent any time on that. The answer is just that.
Mm-hmm. Okay. Very good.
Yeah, I'd like
any other questions?
Yeah, I'd like to ask another one.
Yes, Greg.
Kind of two related questions. So about contrasting and comparing with Kagome lattice systems. I guess, if we're looking for exotic phases like spin liquids, do you think that real material systems that are supported on a Kagome lattice or a triangular lattice are more promising? And, how similar are phase diagrams for, on the theory side for a triangular and Kagome lattice?
Right.
Like the one that you're showing there is
on a Kagome, you have your starting point of 120 is significantly more complicated, as you know, right? So it is the one which again classically has infinite degeneracy actually, and then the spin 1/2 is certainly not ordered. Spin 1 is also not ordered, trimerized. So yeah, you have somewhat different starting ground already at this stage. What I find, okay, so I can tell a little bit more of my other recent interests sort of towards the generalized Kitaev on a honeycomb, rather away from Kitaev point, but you can see a lot of similarity between ordered phases. Basically, you can tell that this stripe phase is essentially the same idea as the zigzag phase here. Like stripe YZ is a zigzag with the tilted, which is tilted outside of the plane. The other one also has a mirror in that model. So ordered phases kind of proliferate in a similar fashion. So the more complicated states, like that, there is more complicated spiral state on the honeycomb, which is funnily it's been known since 1979 for the studies of J1 J2 model, the J1 J2 J3 model. So it's hard to answer such a general question. So just let me tell you, Kagome has potential because it has kind of better starting in terms of degeneracy. You can play with degeneracy a lot. Whether it leads to you anywhere, it's a separate question, and ultimately it's numerics which can tell you yes or no.
Yeah. Okay. Yeah. No, I appreciate that. I was just curious about your general feeling about it. I know it's a hard question. So.
I don't make long-term plans. I diffuse from Kagome to this problem. So.
Okay. Okay, great. Thanks.
Any other questions? All right. If not, I guess I speak for everyone in thanking you, Sasha, for not only the science, but also sharing the history lesson. That was really
if
a nice touch.
If you want to read more, there was a reference there on the top from Physics Uspehi, which is 100th anniversary of Yuri Rumen. He was a great storyteller as well. So he has lots of stories about people you hear a lot more, like Dirac and other people.
All right, I look it up. If it's on your slides, we can all go to the YouTube recording and find it.
I can send to everyone if you want.
All right. Thank you, everyone. And we meet again next week. We're going to have a series of experimental presentations next. So I hope we meet again virtually.
Thanks again.
Have a great week.
And thanks
Bye,
for
Sasha. Thank you.